Yes, questions?
Mass is conserved.
Energy is conserved.
Mass is not conserved.
Yes.
Tamam.
Mass is not conserved in the sense that if you just sum the masses of the particles before they interact and the sum their masses after they interact, it need not be the same. Like one of the questions in the exam was that. So the initial mass of the particles before colliding was not equal to the final mass of the object. Well, you see, what do we know about the mass? This combination, this is equal to E squared. No, sorry, no. Minus E squared E squared minus P squared C squared is equal to M squared C to the 4th. If you know the energy of your system, the momentum of your system, then you know the mass of the system. Other questions? Okay, so let's continue with our particle in a box. Let's just review a bit. We had this, we had such a potential. Well, this is, for example, a realistic case where you have a very thin conductor. The conductor acts like a potential well. The outside is at a zero potential. Inside the conductor, the electrons feel a finite negative potential so that the electrons are inside. So if you send a photon and give some energy to the electrons in the conductor, for example, the electron can have such an energy. If you give this much, at least this much energy to the electron, then you liberate it, and that is what we call the photoelectric effect. So it's not just an academic problem, it's an actual problem. This is quite a nice approximation to electrons in a metal. Yeah, I mean, just imagine a very thin, you see, this is your conductor. So if you imagine the potential, there is no potential, the potential has no dependence in the x or the y direction. It has a dependence along the z-axis. It depends only on z. So you can say that, okay, this is the z-axis. So this is the z motion of the electron, in a sense. And then, okay, to solve it more concretely, what we did was we separated into 3 regions. In region 1 and region 2, we are looking for an electron that has such an energy. So classically, the electron doesn't have enough energy to go to region 1 or region 2, region 3. But quantum mechanics tells us that the wave function in region 1 should have this form. And in region 3, it should have this form with certain currently unknown coefficients. So these are our wave functions. And in region 2, which is classically allowed, the wave function will be oscillating. Where here h bar squared kappa squared over 2m is defined as minus e, and h bar squared e plus u0 divided by 2, no, sorry. And h bar squared k squared, this was equal to e plus u0. And the energy over here is minus u0. So this is how the wave function will look like for the ground state, for example. It has an exponential tail in region 1. And then in region 2, it will have, since it's the ground state, it will have a single bump. And then here, it again has a tail in region 3. Now, from your pre-reports, one of the confusions seems to be, you see, this particle is not moving. The wave function is time independent. It doesn't change with time, this wave function. You see, for the nth state, if it exists, the wave function as a function of time is this one. Psi n of x e to power minus e over h bar en of t. So if you would calculate the expectation value of position, let's say, the average position of this particle, this will be equal to psi n star xt, x psi n of xt dx from minus infinity to infinity. Well, there is a time dependence, but you see in the complex conjugate, we have this time dependence with a plus I. Here, we have that same time dependence with a minus I. So they just cancel each other. In fact, this is true not necessarily for the ground state, but all possible energy, so-called energy eigenstates. If the particle has a definite energy, in that case, its position will not change with time. Its average position will not change in time. Well, you see, the average position as a function of time is time independent. Classically speaking, yes. What do you mean the particle is moving inside? What do you mean by the velocity of the particle? Let me ask it that way.
Particle in the box cannot have a zero velocity, so it should be moving.
Well, what do you mean by the velocity of this particle? How do you measure the velocity? The change of the position. So you need to determine its position. What is the position of this particle? It just doesn't have a position. So what does it mean that the particle is moving? Well, if you have a particle that has a zero velocity or zero momentum, it has a probability of being everywhere. Anyway, let's continue along this line. Okay, one of the weird things about this example is that in region 1 and region 3, the wave function is not zero. There is a finite probability of actually observing the particle at this point or at this point. Well, that will be kind of difficult to measure, because if you try to measure the particle at, let's say, at here, then you will be changing the potential. You will not be really measuring the particle subject to this potential. You are changing the potential. But you see, let's look at a different example. Let's assume we have a, well,
Try to measure that you change the potential.
yeah, measuring device will create an additional potential. But for example, what does that mean? Let's suppose you have such a region. Well, such a region can be created, for example, if you have two very close wires. You have one wire, another wire. If they are very close by, each one of the wires will act like a potential well for the electrons. Now, if you try to put an electron here, Well, its wave function will have, let's say you start with a wave function, you put the electron, put the electron with hand or with some device on this, well, on the left wire. Well, its wave function will have such a form. Then here, it won't go to 0 at the edge, but it will decay exponentially. But now here, exponential decay never goes to 0. So there, when it reaches the second wall, there is a finite wave function. So the wave function has to be continuous. So the wave function will have such a form. So even if you put an electron over here, you might end up having an electron on the other wire. That's the energy levels. Well, I'm just assuming that I put an electron over here with an energy equated to this value. Well, if I want to draw a wave function, I want this axis. So that's why I'm also showing it. You can just ignore that dashed line.
Hocam, koyduğumuz elektron enerjisini biliyoruz ya. O zaman ve bu elektron yukarı hareket ediyor şu an.
Yes, let's say so.
O zaman enerjisinden kesin biliyorsak, biz koyduysak ve hareket ediyorsa o zaman zamanda nerede olduğunu bilememiz gerekiyor.
Well, you see, when we are saying that we know the energy, well, all the energy measurements will have some uncertainty. So basically what I'm imagining over here is, let's just hold the electron somehow. Well, I'm not really determining the position exactly. There will be an uncertainty there. There will be a energy uncertainty also. Let's say that I just position it in such a wire. Or a more realistic example would be just take two wires, very small wires, and bring them very close together, like in circuits, like in electronic circuits, CPUs. One problem with the CPUs, why we cannot really make the CPUs even more smaller, is that if you want to make CPUs much, much smaller, well, the wires, in the CPUs, there are wires. Those wires come very close together. So you are trying to send a current through one wire, but then you end up having a current in the other wire, if the wires are very close to each other. So that's one of the obstacles in making the CPUs smaller and faster.
Her zaman geçtiği yerdeki enerjisi ilk geçtiği yer wave function'ın peak value'su için konuşuyorum. Daha mı küçük oluyor geçtiği yerde?
Well, let's see. In this problem, we start here. We put a localized wave function on the left well. Well, it will spread. So it will have some kind of such an oscillation. Well, in this classically forbidden region, the solution will be exponentially decaying. So when it comes out, the amplitude will be smaller. Well, of course, this wave function, by the way, doesn't have a definite energy, as you had pointed out. It's not a definite energy. It's not an eigenvalue of the Hamiltonian. If you try to solve the eigenvalues of this Hamiltonian, assuming both of these wells are exactly the same, well, technically, conceptually, it's trivial. You see, you have region 1, region 2, region 3, region 4, region 5. Here, it should be exponentially decaying, the solution. Here, in this region, it should be exponentially decaying as it goes to infinity. In this region, it should be oscillating. In this region, it should be oscillating. In this region in between, it should have both the exponential decay and exponential increase, both of them. Because you see, here we know that it should be exponentially decaying, because at infinity it should be 0. But here in this region, it doesn't go to infinity. So we have both the exponentially decaying and increasing solutions. So we can solve in each region. Then, of course, there will be, now the technical part will be complicated. You have many unknowns. You have one unknown here, 2 over here, 3, 2 over here, 5, 2 more, 7, and 1 more, 8 unknowns. You have to write down 8 equations The wave function has to be continuous here. Its derivative should be continuous here. It should be the wave function and its derivative should be continuous here. The wave function and its derivative should be continuous here and also here.
Sağdaki duvar şey değil mi?
That would simplify it. So you have 8 unknowns, you have 8 equations, and you can just go on and solve for the eigenvalues. And it will turn out that the eigenvalues have equal magnitudes on the left and on the right.
Wavelength'leri de aynı demek.
Well, what does the wavelength depend on?
Length olarak
Basically the momentum. The Broglie wavelength will depend on the momentum. What is the momentum? It will depend on the kinetic energy. On the left-hand side and on the right-hand side, they have the same kinetic energy. Sure, it depends on the energy. But then it will not really have a fixed wavelength.
length'e göre
Because the position uncertainty is finite, so the momentum uncertainty will also be finite. So there will be a superposition of various wavelengths, let's say, but still you can identify some well-defined wavelength. Yes?
Süperpozisyonu uygulayabilir mi diyecektim ben.
Yes?
Orada duvarı yoksa ekrana bir şeyler ekleyip çıkartmak.
What do you mean? Just ignore this wall and then add it up? Well, you see, superposition doesn't hold for the potential. If you have many solutions for the given potential, then you can just add them up. They will still be the solution for the given potential, but you are not changing the potential. That doesn't work, unfortunately. Anyway, let's go to a more simple, more realistic case. Let's just ignore these walls. Let's just assume just a single barrier. So this is what we will assume. This is u is equal to 0. And it has some height, let's say u is equal to u0. Now, essentially, you can just think of it as you have some region of high potential, and you keep sending particles. You keep sending them all the time. Now, those particles, they are free. They will have such a wave function. And then they enter the barrier, the wave. It should decay, and then it leaves the barrier. Now, the question I would like to ask is, well, this tells us that if I keep sending more particles to this barrier, classically all of them should reflect back. But quantum mechanics tells me that I will be able to find some of them on the other side. So if I put a detector over here, let's say, this is my detector. My detector is far away, so it doesn't change this potential over here. So that detector will eventually measure some particles. So what is that probability? Classically, it's not allowed.
duvarın kalınlığına göre dikey artacak. Duvarın kalınlığına göre
Sure.
görünme olasılığı değişecek.
Sure. That is what we are trying to calculate now. That's the basic concept. So
Yüksekliği nasıl etkiliyor?
we will see. Now again we have the region 1, region 2, and region 3. Let's write the wave function in region 1. It will be, and let's say we are looking for a particle with energy E larger than 0. Well, in this case, since the minimum of the potential is already zero energy, so the energy will always be 0. But energy is less than u0. So I'm sending a particle whose energy, classically speaking, is not enough to overcome that barrier. So think of it like this. There is a hill, and you just send a mass towards the hill, but the energy of your mass is not enough to just roll over the hill. So what you would expect classically is that your particle will go, it will start climbing up the hill, eventually it will stop and then come back. But in this problem, which is analogous, we will see that the particle will go to the other side. There is a finite probability for the particle to go to the other side. So what is the wave function in region 1? In region 1, it's a free particle. Well, you can say that cosine kx plus b sine kx, where h bar squared k squared over 2m is equal to e. Well, I would rather, let me put primes over there. I would rather write it as a times e to power I kx plus b times e to power minus I kx. Because these two waves, they have a definite momentum. What is the momentum of this wave? Well, what is the momentum operator? This was h bar over I del over del x. Let me add the momentum operator onto e to power I kx. This is h bar over I del over del x, e to power I kx, which is h bar over I. If you take the derivative, it will have I times k e to power I kx. These i's cancel. So b p hat e to power I kx, this is equal to h bar k times e to power I kx. So this wave function describes a particle whose momentum is equal to h bar times k. It is this one. So that part, the particle described by this wave is just moving in that direction. And then there is another wave. This is, what is the momentum of this wave? Minus h bar times k. So this wave describes a particle which is moving in that direction. Well, that is kind of expected. If you send many particles to this potential barrier, let's say you keep sending uniformly your particles, some of them will be moving in that direction, some of them will be moving in the opposite direction. So this describes the incident wave, the particles that you are sending, and this describes the reflected wave. So this is the incident particle. And this is the reflected particle.
Hocam, partiküller volana çarptıktan sonra bir enerji kaybetmesi gerekiyor mu?
Why?
Çünkü belli bir partikül bir tarafa geçiyorsa o zaman kötü olarak enerji kaybetmeleri gerekiyor.
You see,
Onların değişmesi bir de enerjisi.
you see, this is just one particle. This wave is describing one particle, not many particles. Now, the problem over here is, you see, we had discussed the time-dependent Schrödinger's equation. That describes how the system evolves in time. Now, in this problem, if we would, let's say this is our potential. let me make some copies of it. So let's say that I created a wave packet, not a single wave, but a wave packet. So let's say I start with a wave that has such a shape at some initial time. And it has an average momentum, let's say P0 initially. Of course, this wave doesn't have a definite energy. And then what will happen, if with time it will approach the well. It will also spread. Now, at this time, things get a bit complicated. I have absolutely no idea how it looks like for the time being. It looks a bit complicated. And if you wait a bit longer, you will have a wave that will move in this direction, and another wave on the other side that will move in this direction. Because it's a complicated superposition of many waves. That's the superposition of many exponentials. As I said, I have no idea how it will look like. Probably it will not look like this. So this is what will happen with time. Now, does it lose energy? No, it doesn't lose energy. Because energy is conserved. Where does the remaining energy go? Well, you said, oh, some of it went over there, some of it is over here. But you see, this is not the particle. This is the probability wave that has been split, not the particle. So what this tells me is that if I measure the position of the particle, there is a finite probability that I will measure it on this side. And a larger probability, most probably, that I will measure it on this side. But the energy will still be the same because energy is conserved. The potential doesn't change, so the kinetic energy should not change.
Parçacık o tarafa geçtiğinde parçacığın enerjisini de yine korunmuş olarak ölçersek o potential wave'e geçerken bir şey kaybetmediğini nasıl açıklayabiliriz?
Why should it lose? You said, do you explain it in classical physics? Let's say you send your particle like this. No. You just say that energy is conserved. And in fact, we didn't explicitly state it, but in all the problems that we are looking at, you see, why do we define a potential? We can define a potential only if the forces, etc., of the system are conservative. So to start with, we had in fact restricted ourselves to conservative systems. Now, how do we treat, let's say, dissipative systems, like systems which has friction? We cannot. But even what happens in the dissipative systems, in friction, energy is still conserved. But the energy of one mass is now transferred to the energy of all the other atoms. If I just slide this book, the energy of this book is now transferred to the motion of the atoms making the table. So I have to treat all the system together so that I still have a conserved system.
Shouldn't the reflected wave interact with potential wave? So some energy dissipation occurs there.
Energy dissipates where?
At the interaction of the reflected wave with the potential wave.
So, what is that potential wave? You see,
For example, if we think of it as a matter, as a wall, then the electron...
but it doesn't have to be a wall. It's just a large potential region. For example, it can be an electric potential. I don't know.
So ideally there would be no dissipation.
Ideally, no. This is the system that we are treating. In a realistic system, of course, there will be dissipation. But still, the basic ideas of this approach will still hold. But the problem just becomes much more complicated.
Hocam wave ve wave paket dediğiniz bu olay, reşit bol, bunların birleştirilme zamanını canlandıramadım.
You see? Okay. You see, do we see this? Do I see that wave? No, I never see that wave. But what I can do is I can create a light, let's say an electron source which emits electrons. Then among those electrons, I can pick up electrons having a given velocity or given momentum. But of course, all these filters have some error bars. So essentially what I will know is I have an electron that I know its position is somewhat over here, whose velocity has probably has a value close to over there. So that's I have a very well localized electron with a very well defined momentum. Both position and momentum I know. How do I model that? What is the corresponding wave function? Well, the corresponding wave function should look like this one. The best we can have is a Gaussian wave packet. It's a packet in the sense that it's not just a single harmonic wave. It contains many harmonic waves. And it is localized in this region. So I can more or less identify also its position. Of course, this changes with time. Well, how does it change? With time, I chose the velocity such that it moves towards my barrier. And now here we are in our model building. We are building our model. What is going on? I created the electrons. Then I claim that I can model them like this. This packet, this wave, will move towards my barrier. And when it reaches the barrier, well, its shape will significantly change. I will try to send you a simulation of this, how it passes this barrier. But if I wait long enough, I will see that there will be a wave moving backwards and another wave going forward. These are just tell me the probabilities. These tell me that since there is a probability over here, you see, in reality what we do, we send many electrons in that direction having a given velocity. Then we have detectors. We put some detector over here. You see, this is a this is the region of our potential. I send many electrons from my source. I put a detector over here. And I put a detector over here. Classical physics tells me that none of these electrons should go to that detector. But quantum physics tells me that some of those electrons will go to that detector. Most of them will not go to that detector. They will just bounce back and they will be measured by this detector. That is what I will see in my detectors. That is the model I'm writing down in terms of my wave functions.
Hocam, bizde şey için hani böyle diğer karşılıklı normal bir klasik fizikte görmemizin sebebi, karşı duvara geçmemizin sebebi hani çok olasılıkların birbirine kıyasla son derece hani daha çok aralığının açılması gibi bir şey mi?
What do you mean?
Çok daha fazla partikül olduktan sonra artık hani karşı tarafa geçen partiküllerin karşı tarafa geçmiş olma olasılığı hani duvardan bağlanma olasılığına göre çok küçük olduğu için geçmiyor mu diyoruz? Hani sıfıra yaklaştığı için mi?
Yes, that is what we will see. But you see, we don't say that they don't go through. They do go through. For example, if you hit that wall, if you run and hit that wall, the probability of you finding yourself on the other side of the wall is non-zero.
Not close to zero.
But very close to zero. So you have to keep hitting the wall until the end of the universe, probably longer, if you want to make one measurement in which you just find yourself on the other side. So it's highly improbable. But you see, now when we calculate this, we will see that for one particle, the probability is very small. In your case, we are looking for the tunneling of 10 to the power 26 particles simultaneously.
Birden fazla partikül için bir distribution olmuyor mu?
Sure. Sure. We will be.
Hepsi farklı yerde olduğu için daha da düşüyor. Hepsi farklı şeylerde olduğu için herhalde değil mi?
Well, let's solve this problem. And then we can discuss what happens for larger systems.
When you were first explaining, you drew the exponential decay in the potential value.
Now we are going back to our initial description. You see, this is the description of what happens in time. Now, in this course at least, we will not be looking at the time evolution of these wave functions. That is what you will study in quantum mechanics. So, in the questions that we are discussing are systems which have definite energy. They won't be changing with time. So, how can we think of this? Well, we can, let's assume that you don't send a single particle, but you keep sending many particles. You keep sending them one after the other one, almost continuously. Such a system, a fraction of those particles will bounce back, a fraction of them will keep moving. Such a system will not change in time. This is a time-independent system now. And now I am asking the question, what is the probability wave describing this time-independent system? That is what I'm trying to find out now.
Exponential decay yazdığınız zaman onun farkı neydi? Şu anki çizdiğinizden.
This one. Because that's a state with a single energy. This is not a system with a single energy. So it won't be a simple exponential decay. It will be much more complicated. No, not this one. This picture is completely different. Now we will go back to a system which has a definite fixed energy, a single energy state. Here. You see, this is a wave where the position uncertainty is not large. So the momentum uncertainty is also large. So plus the n, we created in a finite time. So there's an uncertainty also in the energy. This is not a state with a definite energy. Now let's go back to states with definite energy. Now, any questions on this? We solved the problem in region 1. Essentially, it's just the sum of two waves. One is describing the particles moving towards the barrier. The other one is describing the particles that are coming back from the barrier. In which problem? In this problem, how do you create a definite energy state? Okay. No. You see, here the electron is, let's say, on this side, the potential energy is 0, right? The energy is the kinetic energy. But the position is somewhat known. The uncertainty in position is not infinite. That tells me that the uncertainty in momentum is not 0, which tells me that its momentum also should not be 0. But momentum determines the energy. So if there is an uncertainty in momentum, there will be an uncertainty in its energy. So this is not a definite energy state. This one is, because you see, I have no idea about where the particle is. So it can have a definite momentum. Various components can have definite momentum, let's say. Well, here, you see, it doesn't have a definite momentum because its momentum can be on the left-hand side, that is plus h bar k or minus h bar k. But still, both of them correspond to exactly the same energy.
Boundary condition'ları sınırladığınız zaman, belirli bir pozisyona yaptığınız zaman, sabitlediğiniz zaman kesinleşmiş bir state oluyor konumda. Yani bu aralıkta dediğiniz zaman.
You are reducing the uncertainty in position. Let's continue. Okay, any questions on this one? You see, some of you were asking why we were doing the exercises with the cellular forms on Monday. You see, we had this system where you were sending your replies. Now, the idea is Okay, let me just give a side note, make a side note. I'm sure I had mentioned it in the first lecture, but watch the lectures by Eric Mazur. Now, the idea is that classical lecturing, in the sense that the instructor comes here and you just passively listen, just doesn't work. It's a waste of time, just for me and also for you. And what should be do is you should be involved in the lecture. But the problem is, you see, for example, in this class, there are lots of questions which I really enjoy also teaching this class. But the problem is the students who are asking questions is, I don't know, 10 students at most. The first row, a few students on the back, and that's it. So the others are still passively listening. So the question is, how can we involve all the students in the classroom discussions? And that is the kind of the idea of with these voting with your cellular phone. So you have to at least discuss with your friend, maybe not with the professor, but you have to discuss, you have to think, you have to think actively, participate actively. So those are just attempts for the time being. We don't really know how to do that. But we are trying to understand how it works. So that's why we are trying it. So for example, in the last 20 minutes, I have been kind of discussing with these 5 students over here, but I see that I'm losing the students on the back. So that's why I'm trying to stop them, and hopefully you will be asking more questions. So let's continue. So we are in region 1. We solve the wave function. Here, by acting with the momentum operator, if you want to identify the momentum of a given wave function, if it has any, you just act on that wave function with the corresponding operator. If the wave function is an eigenvalue, like in this case, then we know that that wave function describes a particle of that momentum. So you see, we know that this wave function satisfies this relationship. And this tells me that this wave function describes a particle with momentum h bar k. So in region 1, the wave has 2 components. One has momentum h bar k moving towards the barrier. The other one has a momentum minus h bar k moving away from the barrier. Classically, that also makes sense. We are just sending many particles in that direction with a given momentum h bar k. Some of them will just bounce back. They will have a momentum minus h bar k. Now let's look at region 3. Psi 3. Well, you see, in region 3, again, the potential is 0. There's no potential. The energy is already fixed. The energy of this particle is h bar squared k squared over 2m. So in region 3, the wave is, again, c times e to the power I kx plus d times e to the power minus I kx in general. But you see, we already said that this wave describes a particle moving in that direction. This one is describing a particle in the opposite direction. But in region 3, there is nothing that bounces my particle back. So my particles are moving in this direction. Some of them will be bouncing back. Those who do not bounce back will just move forward. There is no particles moving toward the left in region 3. So that tells me that D should be 0. So in region 3, this is my wave. Now comes region 2. Let me call it E times e to the power I, kappa x plus f times e to the power minus kappa x. where h bar squared kappa squared over 2m is u0 minus e. You see, I don't have a single one. In principle, I have both of them. Because, I mean, in the previous example of the particle in a box, we just eliminated one of them, saying that the wave function should be 0 at infinities. But here, region 2 does not contain the infinite distance. So there is no reason why this term or that term should be 0. Now, in this example, we said that away from this wall, the wave function should decay and go to 0. Away from this wall, it should go to 0. Why? Because in region 2, I have x is equal to infinity, and my wave function should be 0 at x equal to infinity, or finite at least. In region 1, I have the point x is equal to minus infinity. My wave function should be 0 at x is equal to minus infinity. That is why this term doesn't appear in region 1. And this term doesn't appear in region 2. Here I don't have a plus e to power kappa x term. But in this problem, in this tunneling problem, in region 2, I don't have the x is equal to plus infinity. I neither have the x is equal to minus infinity term. Just another note, for example, the wave function in region 3, at x goes to infinity, the wave function doesn't go to 0. And similarly in region 1, at x is equal to minus infinity, the wave function doesn't go to 0. But in this problem, they don't have to. Because you see, in the particle in a box problem, you know that the particle is in the box. Well, quantum mechanics tells us that it spreads a bit larger than the box, but we definitely know that the particle cannot go to infinity. So that is why the probability of observing the particle at infinity should be 0. But in this problem, well, my particles are coming from infinity. I'm not modeling the source. So the particles, I'm just assuming they are coming from infinity. If they reflect back, they will be going back to infinity. If they go to the other side, again, they will go to infinity. So at infinities, in this problem at least, I will be observing my particles. So the probability need not be 0 at infinities. Because I'm not modeling my source over here. I'm just assuming that my source is very far away. All the detectors are very far away. So that's why in region 1 and in region 3, the wave function does not go to 0. So now we have this problem. Let's say this is x is equal to 0. This is x is equal to L. Now the complete wave function is this one, a times e to power ikx plus b times e to power minus ikx if x is less than 0. It is a c times e to power ikx if x is larger than 0. And I don't have this e to power minus ikx term because there is nothing to reflect my particle back in this region. And in between, no, this is larger than L. And x between 0 and L, I have e to power kappa x plus f e to power minus kappa x.
Why kappa but not k?
Well, you see, in region 1 and region 2, the potential is 0. No, sorry, in region 3, the potential is 0. So the Schrödinger equation is just this one. E of psi.
This potential is zero. Böyle define ettiğimiz için zero değil mi?
Sure. You can just shift the potential whichever way you like. So I define E to be, and keep in mind E is positive. So E can be defined as h bar squared k squared over 2m. Now in region 2, U is equal to U0, which is larger than E. So now the Schrödinger equation is this one. Or if I bring it to the previous form, by dx squared, this should be equal to minus u0 minus e psi. Now this u0 minus e is larger than 0, because u0 is larger than e, and this number I define as h bar, I should use some other k. So that is why in region 2, I have a different equation than in region 1 and 3. Okay, so now we need to determine what this A, B, E, F, and C are.
İkinci bölgeyle reflektif ya da incident part yani wave oluyor mu?
Well, you see, let's look at them. Let's look at the momentum of this wave.
Bölgeyi olacak değil mi?
Hmm?
Bölgeyi yok değil mi?
I have that. This is why I have that minus I. Well, if I would identify a momentum with this particle, it's imaginary. There is no particle over there. I cannot really give a momentum there. But what we can do is we can define a particle flux. And if you define the particle flux in region 2, it's just 0. There is no particle flux.
Probability o zaman
The probability is non-zero,
ona
but the particle flux is 0. So we don't really know how to interpret this in this tunneling region, what is going on there.
What we mean by flux is in the classical way of counterparticles passing through it.
Yeah. There is no flux through the in the barrier. Yes, there is a particle flux in region 3.
How come if there is no flux in the region 2, how can we have a possibility in the second region? If there is no flux.
Why not?
Maybe is it an assumption or experimental thing? Flux
Yes.
being zero?
This is a model we are building and trying to interpret that model. You see, as I said, if you try to measure something inside the barrier, well, you are changing the barrier. So how do you measure what is going on inside the barrier? The only thing we know is what is going in and what is coming out.
So,
Hmm?
oh, okay, flux. No,
We are looking
no
at the-
absorbing the particle.
No absorption.
Does that mean particle goes from region 1 to region 3 without necessarily passing through to region 2?
What does it mean?
Just
You see, you are still imagining, oh, I have this particle, let me just follow that particle. Position doesn't exist. Now, what will be the probability of tunneling? Yes.
Real life dissipation yok mu?
So,
Yani particle exist olmalı ki dissipation olsun.
you see, in a real life, how do you create this potential well? By using many other particles. You have to treat all of them together.
If we assume that there is dissipation, do we have to say that flux is negative?
You see, this model, again, I'm restricting myself to this very simple model. In this model, there's no dissipation, and you cannot put dissipation. It just doesn't, you cannot treat it this way. Well, the probability of tunneling, we can just define it as flux in region 3 divided by influx in region 1. So if I'm sending 1 million particles, if 5 of them passes through, then the tunneling probability will be just 5 over 1 million.
Yani şeyde olması gerekmiyor. Region 1'de gelenler eksi gidenler.
That is why I wrote the influx. If I'm sending, let's say, 1 million particles, if 5 of them goes through, then 1 million and 5 of them should come back. Well, let's see, what is the outflux? This is my wave function. Well, flux basically has two components. One, the probability, second, the velocity. Now, the probability will be given by this C, the amplitude in region 3. It will be C squared times the V in region 3 divided by, well, influx is A. That is what describes the incoming particles. That's just A squared in region 1, the speed in region 1. This is how we define the probability. Well, in this example at least, the speed of the particle in region 3 and region 1, they are the same. So they just cancel. And this is just C squared over A squared. So if we are interested in this probability, what we need to calculate is not C or A independently, but rather C over A. That's what we need to calculate. Well, how do we calculate that? We impose the boundary conditions. So this is our wave. We had already imposed the boundary conditions at infinity, but we also have the conditions at x is equal to 0. At x is equal to 0, my wave function has to be continuous. Well, to the left of x is equal to 0, my wave function is just a plus b. To the right of x is equal to 0, I'm here, my wave function is e plus f. So this is from psi at x is equal to 0 is continuous. And similarly, the derivative of psi with respect to x should be continuous. And this tells me that ik times a minus b should be equal to kappa times e minus f. I just took the derivative of this one and the derivative of this one. The relative minus signs over here are due to the minus signs in the exponents. And then we have also at x is equal to L, psi of x should be continuous. So a times e to power I k L plus b times e to power minus I k L. No, sorry, this is wrong. At x is equal to L, we have E times e to the power kappa x plus F times e to the power minus kappa x. This should be equal to C times e to the power x is now L. C times IKL. And the derivative of psi should be continuous. And that would tell me that kappa times E times e to the power KL minus F times e to the power minus KL. This should be equal to IKC times e to the power IKL. Okay, so these are the equations we need to solve. I will not solve them. But you see, we have 5 equations, 5 unknowns, A, B, E, F, and C, and just 4 equations. Well, normalization will be different. But you see, here we don't really need to solve A, B, etc., all of them. We just need to know C as a function of A, as a C over A. So I can treat A as something known, which we can fix using normalization. But I will not really care about that. So I will treat A as an input, let's say, as a known constant. So I have 4 unknowns, and I have 4 equations, which will allow me to find the C in terms of A. Now, it turns out to be a somewhat complicated expression, but in an approximation, in the approximation that the energy, let's say if E is much less than U0, you see, the energy is far from being enough to overcome the barrier. Then the probability has a simple form. E to the power minus twice kappa L. This is the probability. This one. Well, what I did, I solved these 4 equations for C in terms of A. And then I looked at my expression for C. Then I used this approximation. With this approximation, this is my probability. Now, you see, if you look at that probability, that changes very fast with L. You see, if L is, let's say, twice the value, originally, if the probability is, let's say, is 0.1, if you increase L by a factor of 2, the probability goes to 10%. So this will be, if we have some means of measuring that probability, that will be a very precise measurement of L. Because a very slight change in L will cause a huge change in P. So if you can measure P with a decent probability, that will still tell us what L is with a very high accuracy. And that is what we use in scanning tunneling microscopes. Now, in scanning tunneling microscopes, the basic idea is this one. Let's say you have some surface. And then you bring some very thin tip on the surface. Now, if you would think of this as some potentials, in this conductor, it has to be a conductor. The electron is in a potential well. The electrons on the tip, which is also a conductor, is also in a potential well. So we have 2 regions, this region and that region, which have a low potential for the electron. And then there is this region, which has a high potential energy for the electron. So ordinarily, the electron, if it is over without the tip, if an electron is over here, it just stays there. If the electron is on the tip without this material, if it is over there, it stays there. It's not potential well. This is a region of high potential energy for the electron. But now when you bring them together, now let me just plot the potential energy along this line. You see, along this line, the potential energy looks like this. We have a low potential energy. Let's say this is point A, this is point B. At the point A, the potential energy increases. And then at the point B, it is again decreases. This is what the potential energy will look like along this line. So it's just like the problem we had solved. On one side, we have electrons that are almost free to move. On the other side, we have electrons that are free to move. They cannot move over here. That's exactly the same problem. So what you do in this system, let's say you have your tip. This is your material. You just start moving your tip very slowly. And to move your tip very slowly at very small distances, what you use is a piezoelectric crystal. Well, those are the crystals that you also use when you have your lighters. So these crystals have a nice property that if you hit them, they create a large electric field so that you get the sparks. For example, in the electric ovens, or not the gas ovens, if you go to your kitchen, most of them has this button. Yeah, I mean, those probably work with the electricity of home, but those lighters, when you make that chit sound, essentially something is hitting a very small crystal inside. So that creates a large electric field. That pressure creates a huge electric field, which creates this electric spark. But it also works the other way around. If you apply an electric field to them, or if you just apply some potential to them, creating this electric field, their shape changes. And you can just move objects by microns, let's say. Very slowly you can move objects. And you know how much you have moved. Well, that's quite often what is used. So you get some piezoelectric crystals to displace this tip very slightly to the left or to the right. Then you can basically do two things. For example, if this tip at this height, it comes over here, you see L is increased. The probability will drop. Now, in this case, how do you measure the probability? Well, you apply a potential difference between the tip and what's called your substrate. You apply a potential difference. That potential difference creates a current. You see, essentially, that potential difference will just force electrons to move towards the tip. So they will accumulate over here, and some of them will tunnel. How many of them will tunnel will depend on the probability. So if you can determine the current, then you are measuring the probability. Plus, you don't even need to know the exact current. You see, one thing you can do is you can try to keep the probability constant. For example, if this tip comes over here, L is now much larger. So the current drops. So if you want to keep the current constant, you have to move the tip downward. So that after some time, the distance will be more or less the same. The probability will be the same, so you recover the initial current. But then you know how much you have moved the tip down. So you know how much the surface went down. That is one way. The other way is just you keep the height constant and measure how the current changes. Well, the changes of the current, if you take the logarithm of the current at least, that will tell you how the height of the surface changes. So you can measure the surface.
Does the substrate have to be conductor?
Yes. In this system, yes.
Hocam bizde bundan var mı?
Yes. We have two, I think.
Şey yapıyorlar ya, Week'in elektron mikroskopta örnekleri altınla kaplıyorlarmış. Bunda da öyle bir şey yapıyorlar mı?
Well, it has to be a conductor. You see, these are all not scanning electrons, they're scanning tunneling. You see, these are some actual images. You can see individual atoms.
Hocam olursa eksi kaça kadar falan bunu observe edebiliyoruz? Nasıl bir
Well, let's see, what is the size of the atom?
yani angstrom.
Well, you see, these are atoms. We cannot go below the atoms. I would say the resolution is of the order of angstroms, a few angstroms. And here you have the simulation of the tip. Well, there are various microscopes. This is scanning tunneling microscope. There is the scanning, sorry. In the department, we have atomic force microscopy.
Nerede hocam?
Well, you know, Ahmet Oral, our dean, has a company who is producing atomic force microscopes. I don't know in which lab it is, but I know that he gave us two.
Merkez labda bir tane scanning elektron mikroskop
Yes.
varmış.
Now, the ones we have are this size, atomic force microscopes.
Heisenberg'e göre biz bu yöntemle hiçbir zaman bu şekilde elektronu göremeyeceğiz.
What do you mean? Here we are not seeing the electron, we are seeing the atoms.
Yok, yani görmek istesek bu yöntemi kullanarak elektronu göremiyoruz. Yani atomun daha içine inemiyoruz. Sadece bu kadar oluyor.
Well, you see, we can see inside the atom. You see, we have the uncertainty principle.
Ama zaten elektron boyuta sahip bir şey değil. Biliyor musun?
Point particle diye kabul ediyorsun.
If you, for example, you take the electron in the atom, then you can estimate what it should be, its delta P. If you know this energy, we have already calculated the energy of the electrons. So you can estimate what its momentum should be. And corresponding to that momentum, you can calculate the de Broglie wavelength, which will be typical a measure of the uncertainty in its position. So that is the size of the atom. So the uncertainty in the position of the electron in the atom is the size of the atom. So if you are thinking that, oh, maybe the electron has a fixed position, but we are not able to see it. No, the electron doesn't have a position in the atom.
Potential change'i şeyde nasıl model edebilirsiniz? Şu potential high problemiyle yani potansiyel değişimi böyle yüksekliği neyi değiştiriyor?
Which one you mean? This shape. Well, you see, this is a three-dimensional problem which cannot be analytically solved. And that is why people do numeric simulations to understand what is going on and how should we interpret these currents. But still, the basic idea is not any different. So the idea is that if you have a potential barrier, the tunneling probability will be very sensitive to L. That is the idea. It's the exact expression of this probability. Who cares, to be honest?
Uyla değişiyor.
Hmm?
Uyla değil, potential'la değişiyor.
What do you mean it doesn't change? What is kappa? See, what is the exact solution of A, B, E, F, and C? Why should you care? Why should I care? Does it give us any more understanding? Not really. But of course, if you want to put it in a realistic practical application like the scanning tunneling microscope, you have to understand more precisely how this probability changes with various other parameters. so that you can interpret your result. But at least this much would tell us that this scanning tunneling microscope should work. Now, how do you make it work? That's a different problem. Do you want a break? Let's give a 5-minute break, and then we will continue.